Hello everyone. So we have been discussing about the processor design, and we have seen the basic processor design, and then we started looking into the pipelined processor design. We have also started discussing about some of the hazard associated with pipelined processor. We briefly looked into structural hazard, and we also have started looking into data hazard to understand the different kinds of hazards. Now, before we move to discuss more about data hazard, I would like to briefly uh, revisit the structural hazard part, and pictorially I would like to show you guys that how what do we mean when we discussed about structural hazard in the last lecture. So, the structural hazard part we have already understood that if I have unified memory, so basically the instruction memory and the data memory are same, then the instruction which is trying to be fetched, we are trying to fetch in cycle number 4, will try to access the same memory which this load instruction is trying to, let's say, uh, uh, load the data from. All right. So, in one cycle you are trying to read memory using these two instructions, and that can lead to structural hazard if you have unified memory. So, when we say unified memory, let us try to see. So, we try to understand this through this block diagram, but this block diagram may not be give you very intuitive sense about what we mean. So, to enhance that, we have this simplified diagram of our pipeline stages. Now, it is not exactly what we have discussed in our simple RISC architecture, or the detail of each of these blocks may not be exact, but for a broad understanding, and broadly it talks about the similar things. It is not showing everything which is there in the block, but it is showing the primary things which are important. So, here we have our instruction memory. We are in this fetch stage, and in the fetch stage our PC gets calculated, as well as we read the instruction memory and we find the 32-bit instruction which goes to the decode stage. In the decode stage we have the general purpose registers, where from we get the operands. We can get our required operands from the immediate values as well, and then we have some branch related operations which are not explicitly shown here. And then there is your execution stage, memory stage, where you are primarily dealing with load store kind of instructions, where you are reading the data memory and writing the data memory. And then finally you have write back, where you are updating the register file with the appropriate values. All right. So, this is your first 5-stage pipeline. Now, when we discussed about structural hazard, we said that now this is not unified. So, this is Harvard architecture, where instruction memory and data memory are separate, and you can simultaneously access them. There is no issue. But if we would have a unified memory, then how it will look like. So, we have just modified this block diagram and replace the independent memories, instruction and data memory, with a unified memory here. So, now you see that whenever the instruction need to be read, so the address comes here, and then you read the data, and then instruction goes back to the 32-bit instruction goes back to the instruction register. Similarly, in the memory stage, you get the address, and depending on whether you are trying to read data or write data, so basically whether you are dealing with a load or stored instruction, you will be either reading the data, or you will be sending the data that need to be written into the unified memory. Now you see that because there is only one read port and one write port, so if I try to access this memory simultaneously from two instruction, then it will create data structural hazard. So I hope this makes sense. So have a look at this picture and how unified memory will work, and then if you look at this pipeline diagram, then you see that okay, this load instruction which is trying to read or load data from memory, and this instruction which is trying to fetch data, fetch instruction, they will try to use the same read port, and because of that, since you have we assume that there is only one read port, it will create a structural hazard. All right. So hope this makes sense. Please feel free to ask if you have any questions related to this. Okay. Now going forward, we would like to see, we have already started looking into data hazards, and we have seen that there are different kind of data hazard. So I'll just briefly recap. Read after write data hazard. So the example is here, where one instruction is writing the register, and subsequent instruction is trying to read that instruction. Now since this is a arithmetic operation, the updated value of R1 will be available after your write back stage only, and in between, if you want to use this R1 value, you will not get appropriate data. So that is a problem. Similarly, there can be some other hazards which are and this hazard is also called there is a direct data dependence, and so that's why this is a hazard which we cannot avoid. We have to deal with this hazard, and one of the ways to deal with it is basically you wait for the data to be available. So basically you make sure that you don't proceed till your correct data, correct R1 value is available, and once that value is available, you proceed further. Now this how do you enable it? So there are hardware approaches. So we'll talk about it in few minutes. The other kind of hazards we talked about are write after read hazard. So write after read hazard is basically you are writing this value R2, or basically you are okay. So yeah, write after read. So basically you are writing this value R2 after you have written this. You are writing this value after you have read this in the previous instruction. So so if instructions are executed in order, then this will not create a problem, because you will be reading this value and then only you will be updating this value. So there is no way it can create a problem if you are executing things in order, or if you are not allowing multiple instructions to be executed simultaneously, then also it will not create a problem. Now what do I mean by multiple instruction executed simultaneously? Let us say I have two parallel pipelines, and in those two parallel pipelines both this instruction can be executed parallelly. Now you know that the value which you are reading in this instruction has to be before this updation happened. So now if this is not maintained, then there will be a hazard. so when you are executing multiple instructions at the same time. So this is also called this is called anti-dependence, but we don't have to worry about it right now, because we are not going to have out of order execution as well as multiple instruction getting executed simultaneously. This kind of situation will not encounter now. The other kind of hazard is write after write. So basically two instructions writing the same register file, and this can be a bigger issue when different instructions take different amount of time. For example, if one of the instruction is a multiply, and though it has been issued earlier, let us say this is a multiply instruction, alright. So this will take, let us say, 4 times more execution time compared to a subtract or add instruction. So though this instruction has been issued earlier, this instruction will get executed faster than this. So your R1 will get updated here first, and then later R1 will get updated again. But this is not the actual sequence which the programmer wanted. The programmer wanted the R1 will be updated latest by this subtract instruction, but because this is taking more time, so it might happen that this will create a problem. So to avoid that, you make sure that these instructions do not finally update the registers which are which the destination register out of order. So basically, if you maintain that, then even if this instruction is taking longer, you will wait for this updation to happen, and then only this instruction will update R1. So if you want to ensure that there is no write after write hazard, you have to make sure that you do not allow out of order updation of this register files. All right. Okay. So now let us move ahead and see the ways we can or approaches we can resolve the data hazards. So what we are trying to see now is approaches to resolve data hazards. So the first approach we will talk about is basically called schedule. So basically, programmer looks at the data flow, and programmer explicitly avoids scheduling instructions that would create data hazard. So basically, all the dependent instructions are scheduled in such a way that they will get updated, or their updation will be done before the subsequent instruction try to use them. So basically, scheduling, which is very intuitive. So the onus is left to the programmer. So programmer explicitly avoids scheduling instruction that would create data hazard. Now this is easier said than done, because when you are looking at very complicated and big programs, it's very difficult to keep track of all the data flows and make sure that like you have enough precautions so that there is no no data hazard because of the instructions which you have written. Also, this is very much tied with the hardware you will be using. For example, if some hardware uses, let's say, multiply operation takes 3 cycles in some hardware, another hardware will require, let's say, less number of cycles for multiply, and accordingly uh, the programmer has to have that information, and accordingly he can sequence his instructions. Uh, it also is not very wise, because uh, security becomes there are lot of possibility of security vulnerability, because you are exposing your hardware completely to the programmer, and then programmer or some malicious entity can make use of that and write unwanted programs which can create problem in your system. So that's why this is not a very successful way to avoiding data hazard. A more popular approach is called stall. So it is also sometimes called interlocking. So basically here the hardware includes control logic that will look at the preceding instructions, and if there is any dependence on it, and accordingly it will freeze the execution. So basically hardware includes control logic So basically here you have hardware which will have enough logic, which will look at if there is any instruction which is working or updating some value which is required by the subsequent instruction, then the subsequent instruction will be stalled or stopped till the data is the data value is available. So this is called stall, and using this stall logic uh, we can make sure that the data which we are looking for is available before the instructions are executed. So we will talk about it in more detail in our subsequent discussion. The other approach to address this data hazard is called bypass. So basically in this approach, the result which is getting updated in the previous instruction is sent to the next instruction immediately as soon as it is available, so that you do not have to wait for long duration for the data produced by the previous instruction to be available. So in the example we have seen earlier related to data hazard, we have seen that the this R1 is only finally getting updated in the general purpose register file in the write back stage. So you have to wait till this point, whereas if you look carefully, the result of R2 plus R3, which is supposed to be stored in R1 is available immediately after this execution stage, right. So, it is not written in the register file, but this result of this arithmetic operation is available immediately after this cycle number 3. In cycle number 4, I have the data which I need for R1. So, bypassing says that that instead of waiting for this write back to happen, now I know that after cycle 3 the data is available. So, can I forward, so this is also called forwarding. So, can I forward the data to the next instruction, so that it can start executing, because it is interested in the value of R1, and the value of R1 is nothing but R1 plus R2, R2 plus R3, right. So, this value is available. So, if we can somehow bypass this value to the next instruction, then instead of waiting for the till the write back stage, we can actually start executing in this stage itself. So, without any penalty. So, this is what bypassing is. All right. So, so the definition of bypassing is that hardware data path allows to an earlier stage before preceding instruction has left the pipeline. So, basically before the instruction is completely executed, you are allowing data to be sent to an earlier stage. So, preceding instruction has left the pipeline. So, though it is little verbose, but it should make sense completely, because this is what we are doing here when we do bypassing, right. So, this instruction will be out of pipeline only after the cycle number 5, right. But what we are saying that okay, we do not want to wait till that point, and since the data is available, so we send this available data to an earlier stage, which is the execute stage, because the add instruction now will move to the execute stage, and we are in the memory stage, we have the data. So, from memory stage, if we can send or send back the data or bypass the data to execute stage, then then we can start executing this instruction, and this we are doing before the preceding instruction has left the pipeline. Okay. So, this is what bypass is. So, we will talk about it, each of these things in more detail in our subsequent discussions. And finally, there is another approach to handle the data hazard, which is called speculate. So, basically it's not very foolproof method. So, what we will do, we will guess that there is not a problem if incorrect. So, as long as so you will not, so in this case you will not stall, and you will speculate that the whatever value R1 has currently, that will be the correct value, and you go ahead and execute without stalling. Now, if later on you realize that you have taken a wrong value, then you have to redo this instruction, and you have to kill whatever you have done, or whatever you have done, you have to erase that and redo the thing. So, this is also another approach which is called speculative, but again speculative approach is not very popular. So, we will just for sake of completeness we are discussing this. So, speculate If your speculation is incorrect, then you have to kill. Incorrect, then kill speculative instruction. And restart. So this speculative thing for data addressing data hazard is more popular, or like sometimes used in out of order processor. So it's not very relevant for us at this point. Okay. So we have already looked into the data hazards. Now we need to figure out. So scheduling we have briefly talked about. So the programmer has to look at the data flow and ensure that the instructions are paced such a way that there is no data hazard. But as I mentioned, like, it becomes very difficult, and also you need to expose the hardware to the programmer. It is very well tied with the hardware, so you will not be able to write compatible programs which can run in different machines. So all these challenges are there. Now, most popular approach to deal with data hazard is basically stall or interlocking. So as the description says, that you have some hardware control logic that will freeze the earlier stages until the preceding instruction has finished producing the data value. So we will try to understand this in little with this with some figures. So essentially, to have this stall mechanism in your hardware, you need some kind of feedback from later stages, so that you know that what kind of registers or what kind of variables the later stages are updating. So basically, later stages provides some dependence information to the earlier stages, and depending on that, the earlier this earlier stages, which are, let us say, in the fetch stage or decode stage, they can decide that whether to stall or not. Now, coming back to this example again. So from this example, we know that the destination register R1 is getting updated. Now, as soon as you fetch this next instruction, you see that one of the operand is R1. Now, if this previous instruction has given a feedback that, okay, see, my destination register is R1, so I will be updating it. So this information is fed to the earlier stages. Now, the earlier stages will look at this instruction and see that, okay, it wants to use R1, but from the feedback from the earlier stages, it is clear that R1 is getting updated. So if this condition matches, that, okay, the destination register which is supposed to get updated by earlier instruction and the current operands are same, then there is no way but you have to wait till this updation is done, this destination register is updated. All right. And the condition, the stall logic actually looks at this condition, that what are your current source register and what are the previous destination registers which are in the pipeline, the instructions which are in the pipeline, what are their destination registers, and if there is a match, then you have to carefully look at it and figure out, like, whether you have to stop your basically stop allowing this instruction to move ahead, and that is where this stall instructions comes. All right. And this can be enabled by some feedback mechanism to the previous stages, so that so the current stages know that okay, what are the operands which earlier instructions are updating. All right. So this is absolutely important. Okay, so just to summarize what we have discussed about the feedback part. So um, so basically feedback to resolve hazards. So we are talking about data hazard only. So basically later stages provide dependence information. To the earlier stages which can stall. Now stalling is one thing. Sometimes you might also have to kill instructions. So basically stall or kill instructions. So when you have to kill instructions, we will talk about it to address control hazard. So basically if you uh, speculatively fetch some instruction and later on realize that this instruction you are not supposed to execute, then you have to kill that instruction or replace that instruction with a no op. Now controlling your pipeline, so this looks very intuitive. So basically you have to check the destination and source registers, and if there is some commonality you have to see what kind of dependence is there, and if that dependence is something like read after write dependence, then you have to stall the subsequent instruction. Now controlling the pipeline in this manner, it will work provided that the later instruction is completely independent, or they do not depend on any of the previous instructions. So just to tell you in more simpler language, so here this kind of feedback for stall operation will work if this instruction is no way dependent on this instruction. So this will go independently and this will go independent. Basically this will still be dependent because it will depend on the value, but the previous instruction is no way dependent on the on some later instruction. Because if that kind of dependence is there, so why it is important? We are talking about having feedback, right? So feedback means I'll just try to draw the 5 stages here. So basically you can imagine that you will have feedback from all the stages. So I have some feedback from here which I will be maybe feeding here. Again I will also feed this feedback to the later stages and so on. So basically there will be feedback path. Right, and so on. So this feedback is required for stalling the instructions, etc. But now this will be fine if there is no later on instruction, basically some instruction which is, let's say, in the write back stage or memory stage, they are not dependent on any of the previous instruction which are in the, let's say, fetch stage, decode stage, etc. Why it is important? Because if that is the case, then there is a possibility of creating a deadlock. So, basically you will be giving some feedback, and then you are waiting for some instruction which will provide you something from here, and then you will be forever waiting, because this will wait for this feedback and this will wait for the feed forward. So, you can't have this thing, and that is why and it will create a deadlock. So, you do not want that. That is why it is important that there is no dependence among the previous instruction with the earlier with the latest instructions. Okay. So, I hope this makes sense. All right. So, now we will look at, we will go back to this read after write hazard, and we will look into this pipeline diagram here. Now, we have seen that if we can somehow detect that there is this dependency, we can stall this instruction till the data is available. Now, what could be the stall logic? So, the stall logic is a very simple, basically not that complicated, at least if we look at it intuitively. So, stall logic is having this. So, if I consider this control logic as your stall logic, so it will have feedbacks from earlier stages about their destination registers. So, destination registers we generally denote by RD, and then from the decode stage we will get what are the source registers. So, basically RS1 and RS2, right. Now, here I can compare. So, is RS1, RS2, or is any of these RS1 and RS2 is same as the RD? If that is the case, then you have to generate the stall signal, and what this stall signal will do, it will make sure that the instruction which is in the decode stage, it does not move ahead, because your OP1 and OP2 are not available yet. You remember your decode stage. So, in the decode stage you were basically looking at your sources and the source registers, and you were figuring out OP1 and OP2. Now, if from the feedback path, so this feedback path can come from different stages from different stages of the earlier instructions. So, I will just try to draw, or I will show you this block diagram, which will make it little more easier. So, what we are saying, that we will have a stall logic here. All right, stall control logic. Now, the stall control logic will get feedback from your this stage, then you can get basically depending on where all your data are getting updated, etc. So, you can get this feedback value. So, this feedback value will tell you that what is the destination register, and from here you will get the source information, and if they are same, then you will generate the stall logic, and you will make sure that basically whenever this stall information stall logic is high, you will ensure that nothing moves forward. So, you remain in this decode stage, and you do not allow the subsequent instruction to be pushed towards the decode stage. All right. So, this is very intuitively what the stall logic looks like. Of course, this is a very simplistic overview, but I think for our understanding at the broad level, this is good enough. All right. So, what it is saying, it is basically showing you the hardware that can implement it, and once that is implemented, then we will have this kind of situation wherever at the decode stage we see that okay, there is a data dependency and we do not have the updated value of register. So, we will stall the process, and if I have subsequent instruction, then what will happen, the subsequent instruction will also stall. So, basically the next instruction will be fetched, but it will not move ahead. Similarly, the other instruction will not be fetched also, because your fetch unit is not free. All right. I hope this makes sense. All right. So, next thing we would like to discuss is about bypass. So, bypass is another technique where we would like to see whether we can reduce the penalty, right. Because we have seen that if there is a stall, then it takes time and we have to wait for that stall to get resolved. Okay. So, to understand the bypass, we can go back to our previous example. Okay, let me remove this. So, this is the example I am trying to get back to. So, now if we look carefully in this instruction, and let us say this is your instruction 1 and this is your instruction number 2, all right. Now, when this instruction number 2 will require the value of R1, this value of R1 is required in the execution stage, when instruction 2 moves to execution stage, right. Now, some of you might get confused that is it not required in the decode stage? It is required in the decode stage, but you are not using that value in the decode stage, right. So, you will be using this value in the execution stage only. Now, if you look at this instruction, so this is very important. So, to have a clarity, what we are saying? We are saying that this add instruction will require the actual value of R1 in the execution stage, though we are trying to basically, though from our previous discussion it was clear that in the decode stage itself all the values should be ready, but yeah, that's true, but the value will be used in the execution stage only. Now, if you look at instruction number 1, this instruction, when will it produce the value of R1? Now, a very straightforward answer can be the value of R1 will be updated or produced at after write back. But if you look at it carefully, actually after write back R1 is getting updated, but the value which is supposed to be stored in R1, that value is available immediately after the execution stage, right. So, end of execution stage we have the updated value of R1. So, now this observation leads to some interesting conclusion. So, now the value I need for instruction 2 is already available after cycle number 3. So, why I should stall everything till cycle number 5? As soon as the value is available, can I make use of that value so that I can improve my performance? So, that is what this bypassing or forwarding strategy says. It says that okay, your value is available after execution. So, can you forward this value to the next instruction or the previous stage, so that the next instruction can use this value. So, basically since the correct value is available here, so we can decide to forward it to the next instruction. So, so this is one example where the value is getting updated in the execution stage, but there might be situation where, let us say for a load instruction, for a load instruction the value will be available, the load value will be available after the memory stage, so in those cases you can even think of bypassing after memory stage, so after write back stage, etc. So, basically we can add multiple forwarding paths. So, and obviously you want to forward the data from later to a previous stage. Okay. Okay, so now let us look at it a little bit pictorially. So, if I want to have forwarding in this case, so the specific example we talked about. So, after the ALU the value is already available, and the next instruction if it can use this value. So, so one way to do that is basically this ALU outcome is fed here as an input to a multiplexer. All right. So, now if you want to use the forwarded value, then you have that value available and you can execute it. And with forwarding, if we write down the couple of instructions which we have seen earlier. So, with forwarding the instructions will look like this. You do not have to wait for several cycles before the data can be used. So, basically we looked into these two instructions. So, add R1 R2 so basically this is our cycles and so on. So, this is with bypassing, with bypass or forwarding. So, it will be fetch, decode, execute, memory and write back. The next instruction, it will be fetched, decode. Now, you see that after the instruction is decoded, in cycle number 4 the value of R1 is updated. So, if I have bypassing, then I can directly jump to execute. I do not have to wait for the data to be written back, because the result of this addition is available at the end of the execution stage, and that I can use directly for my subsequent ALU operation. Okay. So, in this way we have addressed the problem of stall. So, we do not need to stall instruction, because the data is available and we can make use of it. Okay. I hope this makes sense. So, what we have done? We have forwarded the value of R1 after this execution stage to the next stage in this way, so that the next instruction can select this value as one of the operand and execute. Okay. Okay. So, as I mentioned, like the forwarding path can be from different location, and but you really do not want to forward from all the stages of pipeline. So, for example, you can think of forward the data from here, forward the data from here, forward data from every possible position. Now, that can lead to lot of overhead, and your individual stages will also be slowed down. So, you do not want to overdo this forwarding. Okay. So, we have talked about basically the stall and bypass, and we will not talk about speculate at this point, because we are not talking about out of order processors or multiple pipeline processors, etc. Okay. All right. So, so the next thing we would like to talk about is control hazard. Okay. So, we know that the next PC, or basically we always calculate the next PC as PC plus 4. But if there is a this is not true for all the instructions, right? Because we have seen that there are instructions like jump, unconditional jump, there are instructions for conditional jump, etc. And in these cases, the PC, the next instruction where it need to be fetched is not PC plus 4, it is the jump destination. And because in the pipeline we tend to fetch instruction one after another. So, if there is a change in the execution order, or if there is a change in the sequence at which the program is getting executed because of, let us say, this kind of branch instructions, etc., this can lead to basically hazards in the pipeline, and that is called control hazard. All right. So, what we are trying to say here is that, let us say I have instructions like a couple of add instructions. All right. Okay. So, now if I draw the pipeline diagram of this add instructions, so these are the cycle numbers and so on. So, we are fetching, decoding, executing, memory, and write back. Now, think about it. While I have fetched this instruction, I have no clue what this instruction is. When I have decoded in the decode stage, then also I do not know what this instruction is, because I have not read those 5 bits which are denoting the opcode. So, now without knowing, so let us say I want to make sure that I do not do something wrong. All right. So, objective is that I will have pipeline, but I do not want to do anything wrong wrong in this implementation or in this pipeline. Now, if that is the case, then you see that at the decode stage also, you do not know whether it is a branch instruction or not. Even if you know if it is a branch instruction or not, you do not know the outcome of the branch. Let us say you figured out that this is a branch instruction, but this is a basically conditional branch instruction. It is trying to do something like, let us say, branch if equal to this location, branch if equal to 0 to this location, or branch if equal. Now, so at the decode stage, you only know that, okay, it's a so you are not doing anything, because if you remember in your decode stage you were giving out only OP1, OP2 and the immediate and offset values, etc. But whether that branch is taken or not, that is evaluated at the execution stage. Now, if you want to wait till execution stage before you are sure where from your next instruction has to be fetched, because before that you are not sure like what will be the, if first of all if there is a branch instruction, what will be the branch outcome, that becomes clear only when you are in execute stage. Now if you do not want to do things speculatively, then what you have to do, your next instruction, whether it is PC plus 4 or some branch target, that will be only clear in the execution stage, right? So you can fetch the next instruction only after execution stage or only at the execution stage, because in the execution stage you will know that okay, the what is the outcome of the branch, and if it is a new address or a new branch target, then accordingly your PC will get updated and you can start fetching from execution stage. Now you remember that our initial discussion of achieving CPI of 1 in an idle pipeline situation was based on the fact that we will be fetching new instruction every cycle. Now because of this restriction that I do not know where the next instruction will come from till I reach execution stage, so my CPI will be down significantly, because now you see how the pipeline will look like. So I will be here in fetch, then decode, then execute, then memory, and then write back. So you see that this is 5, 6, 7. So I am much small, I am doing things much slowly compared to a fully pipeline stage. Here the CPI will be half compared to what I would have achieved otherwise. So the next instruction also, let us say instruction number 3, so that also will be fetched at this point only, because till this I do not know the fetch the PC location and so on, right. So this will severely impact my performance, because I will be achieving half of what I could have achieved. Now why I am doing this? Because I do not want to fetch some instruction which I was not supposed to fetch. Okay. So one way to address this problem or address this issue of performance is that you start speculating. You speculate that okay, your next instruction will be PC plus 4, and with this speculation you start fetching new instruction, and basically you start executing them. Now what happens if your speculation is wrong? Now your speculation, if your speculation is wrong, then you have to kill that instruction which you have speculatively brought in. Okay. So what we are saying? We are saying that instead of waiting till execution stage to get the next PC accurately and then fetching the instruction, it will impact your pipeline significantly or your performance significantly. The other way can be you speculate. You speculate that the next instruction is, or next address is PC plus 4. Okay. So let's look at one example. So let's say this is your instruction 1, 2, 3 and 4, and these are the different memory location where these instructions are stored. And these are your instructions. So add followed by, let us say, jump to a new location. So this is unconditional jump, then there is add, and then there is on more add. Okay. Now what will happen? So you will be fetching this instruction. So if we draw the pipeline diagram, so you will be fetching, decoding, executing, memory, write back. You will be fetching here, you will be doing these things. Alright. Now speculatively, since we are following the speculative approach, as we are speculating that the next instruction or next address from where PC needs to be brought in is PC plus 4. So with this speculation, we will go ahead and fetch the next instruction as well, and we will move now in clock number 4 or cycle number 4, you are already in the execution stage of this instruction, and you realize that okay, this is a jump instruction and this is the destination from where the next instruction has to be fetched. So as soon as you realize that, you know that you have speculatively fetched some instruction which need to be killed, because this instruction is not supposed to get executed at this point. So what you have to do, but you have fetched this instruction in the pipeline. So you can kill. So the way you have to deal with it is basically you kill this instruction. So you have a logic which will replace this fetched instruction with no op. So basically you will write no op for next subsequent stages. All right, and then you will update your PC accordingly, and the next instruction will be fetched from your this new location 304, and you will again do fetch, decode, execute, and so on. Okay. All right.